Hello friends, welcome to this session. So in this video, we will be looking at very interesting, simple and important concept of PID controller. So being a control engineer, we should understand what do we mean by the controller tuning. So how we can tune the PID controller parameters. So in this video, I will be explaining how we can make use of MATLAB to tune our controller for a given plant. So let's get started. So this is a simple PID controller block we have. So this is our feedback. This is our plant. Okay, P of S, any general random plant we can take. This is our PID controller. This controller now we are tuning. Okay, so this is our reference input. This is the error, and this is the desired output we have. Very simple, and we have the unity feedback here. Okay, these are very famous two equations of your PID controller, that is a Kc E of t plus Kc by Ti integration of E of t dt plus Kc Td det by dt. Okay, so if I replace this Kc by Ti and Kc into Td by the integral and the derivative gain, so the equation becomes, so Kc is replaced by Kp, so the equation becomes U of t equals to Kp Et plus Ki integration of E of t dt plus Kd det by dt. Okay, so getting these values, getting these Kp, Ki, Kd values is nothing but the tuning of PID controller. The suitable values of this Kp, Ki, Kd will drive this output to the desired set point. Okay, so let's check what are the tuning methods we have. So these are very two famous tuning methods we have. One is the process reaction curve method, and another is the ultimate gain and ultimate period method. So in this video, I will be explaining the process reaction curve method. So what is this? So in this method, the process reaction curve is generated in response to a disturbance. Okay, so what we do in this feedback plot, in this total plant, what we do, we give a small disturbance at the input side. We give a step response and we check how my system, how this plant behaves to this step input. Okay, so in that case we don't have this controller, of course, so that this plant is in open loop. Okay, so this is what we have the plant, and we are giving a small disturbance as the input, and we are checking how this plant is behaving to this step input. Okay, we'll get some response like this. Okay, so this is nothing but, this part is nothing but the process reaction curve. Okay, once we give this small disturbance, the output of this plant is known as the process curve, and this is a reaction to this step input. This process curve is then used to calculate the PID parameters. Okay, and this method is performed in open loop. As I told you, our plant is in open loop, so this is our P of S. Okay, here you are giving the step input disturbance and you are measuring the process reaction to that step input. Okay, so this is, we have the output there. So this is the type of the process reaction curve most of the system gives. Okay, so this is what is the S-shaped process reaction curve we get. Okay, so this K is nothing but the steady state value of the open loop plant. This L, okay, see here in this, once you get this process reaction curve, so this black one, this curve is known as a PRC. So this is a PRC. Now our first step is what? You draw a tangent to this process reaction curve. You get the tangent. Now where this tangent intersect to the time axis, this duration is known as the lag in your system. Okay, so L stands for your lag in a system. And the same tangent, it intersects to the steady state value also. Okay, so it intersects with the K point, and this time duration, okay, this time duration we note here. Okay, and the difference between this time and this lag is nothing but our time constant of my system, Tc. Okay, so what we get parameters, three parameters are very important from this process reaction curve. One is the lag of the system, another second one is the time constant, and the third one is the steady state value of this process reaction curve. Okay, so once we get these three parameters, now getting the values of Kp, Ti and Td means what? We'll get here Ki and Kd. So once we get these parameters, so L, that is tau, and K, we can easily find out the Kp, Ki, Kd values. Okay, so if you have only P controller in the plant, then the Kp becomes tau by L. The tau is nothing but time constant. Pi becomes 0.9 tau by L, L by 0.3, and PID becomes 1.2 T by L, and the Ki becomes 2L, and the Kd becomes 0.5 into L. Okay, so this is a Td and this is a Ti. Okay, so Ki will be what? It is a Kp times of Ti, and here Kd will be what? It is a Kp into Td. Okay, so using these formulas we can easily get the values of Kp, Ki, Kd. Okay, so let's try to take one simple example in the MATLAB, and we will try to tune our PID controller. Now let's take one simple example. Take any random system, okay, and let's see how we can use this MATLAB to design our PID controller. Okay, so let me give the title here. So this is the simple program for PID tuning using which method we are looking at? Using process reaction curve. Okay, so what we require first our complex variable s. So it's s tf of s. So let's define one simple system. Okay, so system, so you can take any random system here. So I am taking the two pole system. So one is at -10 and other is at -20. Okay, so you can take any system. Now what we require, I want to get the process reaction curve for this system. Okay, so how we get? Just give a small step response to this system and you will get the process reaction curve. Okay, let's see, let's run this. So step of system. Okay, so it's running. So this is what we have just get this plant, that is 1 by s plus 10 and s plus 20. I think we get the result. Yes, perfect. Okay, so see this is nothing but your process reaction curve for a given step change. Okay, now if you see, it is having some lag. This is of course in S shape, and the steady state value is S 5 into 10 raised to power minus 3, and definitely it is not a desired output. Okay, what we are expecting, our output should be at 1. Okay, so now let's try to develop the PID controller for this. Okay, once we get this step system, now our task is to find out what to find out, that is L, K and tau from PRC, process reaction curve. Okay, so here I told you that, so we have to find out, so this is our process reaction curve. Okay, and we have to find out these parameters, that is lag, time constant and the steady state value. Okay, now go to this figure and let's try to get the tangent. So here we go. So the accurate tangent you draw, the accurate parameters you will get. Okay, that's why I told you initially that this is totally the approximate method of tuning. Okay, you will not get the exact values of Kp, Ki, Kds. Okay, perfect. So it seems to be okay. So this is what the tangent for my PRC. Now let's find out, so where this tangent intersects this time axis, so that point I want to find out. So let's have this point here. So what is the coordinate of this point? It is a 0.0173. okay, so this tangent intersect the time axis at 0.01. okay, so let's have that. So our lag in system is 0.01. perfect. Now what is K value that we have seen? That is a 5 into 10 raised to power minus 3. It is 0.005. and let's have the time constant tau. So from figure, the tau is what? It is the difference between, okay, so it is the difference between this time and this time. Okay, so this time is what? It is nothing but the intersection of tangent to the steady state value. Okay, so let's have the intersection of tangent, this tangent to this steady state value, it is somewhere here. Okay, so let's have that point also here. Perfect. Okay, so this point is nothing but our last limit of your time constant. Okay, so what is it? 0.225. so this is nothing but 0.225. so what is your time constant? Is 0.225 minus 0.01. okay, so I hope it is okay. So 0.225 we will take, so it is 0.22 minus we have L. Okay, so these are the three parameters we get from the process reaction curve. Now what is our next task? Is calculate Kp, Ki, Kd from table. Okay, so we have seen the table, so this is the table and we want to find out the Kp, Ki and Kd. Okay, so Kp is what? It is a 1.2 tau by L. So Kp is equals to, it is 1.2 into, so it is Kp is equals to 1.2 into tau by L, tau divided by L. What is Ki? Ki is nothing but it's a Kp by Ti. Okay, so what is Ti? In this case is Ti is nothing but 2L, so it is divided by 2 into L. Very good. Next we have is a Kd, which is nothing but Kp into Td. Okay, so Kp into, let's check what is Td, is 0.5 L, so it is 0.5 into L. Okay, so these are the values of Kp, Ki, Kd we get. Okay, so now let's save this and let's get the PID controller. So PID controller is equals to, so we have a syntax PID, pass the variables Kp, same variables we need to find out, pass it Kp, Ki and it's a Kd. So these three variables. Okay, so these three variables I am passing. Okay, so now let's save and let's run it. So what we are getting, see here, yes, so this is what the PID controller is, and this is the fashion, and these are the three parameters Kp, Ki and Kd. Okay, so it is a continuous time PID controller in parallel form. We have three forms: parallel, series and ideal one. Okay, now what we get, so let's come back to this PPT and let's see here. We get this point now, controller ho gaya abhi design. Okay, now plant and controller. Now let's take one complete open loop transfer function of these two. So that can be get easy system open sys is equals to series of PID controller and our system. Okay, so this gives me the open loop, complete open loop transfer. There is a multiplication of PID and our system. Now let's take the closed loop of closed system. So this is nothing but feedback, which is a syntax to get the feedback of your open sys, comma, we will take a unity feedback system. Okay, very good. Now we get this complete block diagram. This complete block diagram now we have designed. Okay, which is nothing but closed sys. Okay, now our task is to check out the step response of this closed sys. Now what we are expecting, so this should be properly tuned one. So this should be our desired output. Okay, so let me have two different figures, figure 1 and here we have the figure 2. Okay, So let's save and let's run it, and if you see, perfect. Okay, see here. So let me keep these two figures side by side so that we can easily differentiate. Okay, yes. Now see here, this is figure 2 is what it is, the step response to your open system simply without any controller, and this is with the PID controller. Here the steady state value was 5 into 10 raised to minus 3, but with the PID controller our steady state value is what it is 1, and it is settling near about 1.4 seconds. Okay, and this is settling at 0.7, but definitely we have a very large steady state error there. Okay, so it is nearly equals to 0.005 means it's nearly equals to 0. Okay, so as I already told you, this is what totally approximate values of Kp, Ki, Kd. Okay, if you want this overshoot to be minimum, so we need to change the Kp, Ki, Kd values. Okay, we need to have some different permutations in those values. Okay, so this is the way in which we can make use of the MATLAB, and we can find out the approximate values of Kp, Ki, Kd. So what are the values we get for Kp, Ki, Kd? So you can check this. So Kp is 25.2, Ki is this, and Kd is this much. Okay, now if we simply increase or decrease, okay, now you know the basics. So okay, Kd will speed up your response, Ki will increase your overshoot. So like that, this will affect your system response. Okay, but in conclusion, what I can tell you, using the MATLAB for the PID controller tuning is very simple. Just use few steps, follow these steps, and you will get the approximate values of Kp, Ki, Kd. Okay, so I hope this is clear to everyone now. Okay, so what we have covered, yes, so we have made use of this table. Okay, so in the next video we will check out this ultimate gain and the ultimate period method. Okay, so I hope this video helps you. Okay, so we will meet in the next video with the ultimate gain and ultimate period method using MATLAB. So don't forget to watch that video. Thank you.